Okay,
Hello.
the next speaker is Erhard Steffens.
Thank you very much for inviting me. So I want to present a subject which is somehow related in the polarized gas targets in Europe, but it's also, of course, about my scientific relation with Willy, and about the contributions he produced for our field. Okay, so Willy's idea, I will go through different subjects. Willy's idea of the storage vessel, then the initial feasibility studies by Willy and others, which this was partly covered by Tom, and I will keep my comments short. Then polarized gas targets in Europe, not a full list, but the important ones, and personal remarks about Willy. Okay, so the starting idea was already mentioned in Tom Clegg's talk. It's a comment in one of his papers to the, oh sorry, it's really very, very small. It's probably not readable for me. Okay, so a comment in a paper for the second Polarization Symposium in Karlsruhe in 1965. And so he commented on a method proposed by Savoyski, how to create a polarized beam for injection into an accelerator. And the remark he made is, in practice, this foil, it might consist of a storage container. How can I against this noise?
You want it less louder?
No, not louder, maybe less.
No, it's off. Can you tell me what the problem is? You want it more?
I hear a tone, yes. The echo or whatever.
Can you talk?
Yes, 1, 2, 3, 4. Yeah, I think it's better. Yes. Okay, so in practice, this might consist of a storage container of polarized hydrogen atoms, like Ramsey's group uses for the hydrogen maser, or an optically pumped alkali vapor. This is, of course, another idea which has been applied. Now I learn about this. The experimental demonstration of this idea was done by his group and presented to the Santa Fe polarization meeting in 1980, which was also already shown by Tom. So this test experiment, the test experiment to demonstrate the polarization of these atoms injected to the storage vessel and measured by an alpha beam. The result was that after a long storage time and with about estimated number of wall collisions about 600, the polarization was more or less complete. So the conclusion was that the hydrogen atoms keep their polarization during several hundred wall collisions. And in 1984, there was a workshop on nuclear physics with stored cooled beams with Hans Otto Meyer And this was in parallel to the construction of the IUCF cooler. And Willy talked about free and stored atomic beams as internal polarized targets. And he presented a first idea how such a storage cell could look like, with rather narrow openings for the circulating beam and also for the injected beam. This gives, of course, a high number for the target density. So this had to be modified a bit, but this was the idea how such a storage cell could look like. So he recommended strongly the combination of storage rings with windowless gas targets, that this would enable new experiments. At the same meeting, I talked about storing and cooling of polarized ions. So principle of storage cell was already presented. I think I can just let you look at this diagram in another color, but it's the same simple theory to understand what the thickness of such a storage cell is. Here you see that the storage, the area density T scales with length squared divided by the radius of this beam tube to the third. So it's a strong effect. Density gain compared to a jet without cell can be of the order of 100 or even above. So I want to go through some experiments in Europe based on polarized storage cells. First, the filter target experiment, which where these ideas were tested for the first time, so combination storage cell plus storage ring. Then another development started in 1988 or even before, internal target experiment Deuteron for Web3 at the Butker Institute for Nuclear Physics at Novosibirsk. Source and detector was by the lab, target cell by Argonne National Lab. And then the other experiments I want to discuss, of course, Hermes, the Anke target, PAX target. I will not say anything about the EDM measurements. This is something Frank will explain tomorrow. And then the last, my last topic is the attempt to produce an internal gas target, if possible, polarized for the LHC at CERN. So this is the Filtex proposal. So after a stay of 1 year, I came back to Heidelberg with the idea, which we of course had discussed during my time at LIR. LIR is a storage ring for antiprotons, where one can slowly extract antiprotons and provide a hall with different antiproton experiments. One can also use on an internal target the so-called jet set. And that was a place where we hope to be using the Filtex target. And here you see also two names from this place, Willy and Tom, and then other people from the Filtex collaboration. In '88, there was an international symposium for high energy spin physics, and Willy and I organized a workshop, polarized gas target for storage rings. Willy gave the final report on this. So there were first positive results reported on an Argonne Novosibirsk test experiment, a storage cell in the Web3 electron storage ring, which was very important for our future. and practical realization of storage cells for experiments were discussed. Okay. And 3 years later, we had a workshop on polarized gas targets in Heidelberg. Here are the participants. This is Willy, this is me, and Kirsten Zapfe. Frank is one of the tall guys, yeah, of course. Okay, Willy, yes, there's Erhard. And here during the discussion with the machine, this is part of the newly built storage ring, the TSR, test storage ring, with some participants, for instance, Joe Vandenbrand, people from NICEF. And this was the target we had already built and tested with an external beam. And we had a good feeling that it will work. This is this test storage ring, which was built as a project of the Heidelberg Institute. So this was shortly after completion of this ring. There are still some empty straight sections. This is reserved for the electron cooling. This for the target. Here there's a RF cavity. Here's the injection straight. And this is the Filtex target, which in the installed position. The target was built according to Lear UHV standards, which is a huge hurdle. For instance, you have to use vacuum-fired stainless steel and so on. The technology was partly just taken over, or we even use the equipment at CERN. It's bakeable. So this is a target chamber where the storage cell sits. This is a source. The beam is injected from the side. Here there are two differential pumping stages. And here are the low beta quadrupoles. And this is, so to speak, the PhD work of Frank, together with other grad students. Here's other famous picture. It was also on the title page of our journal of the Physical Society. The view into the target chamber through a Kapton window. The light is from the ion gate, so it means it was evacuated and one could really see inside. This is the last magnet of the source. Here's a T-shaped storage cell, and here's a huge cryopump. Here is a schematic, a little bit turned around. I mean, it's just not totally in coincidence with this geometry here. So the beam, the circulating beam, runs through the beam of the T-shaped storage cell. And then one has 4 detectors behind Kapton windows. And this was one of my really memorable moments in my life. So when we switched this on, then say after 1 hour, one could tell, okay, it's a big success, because the effect was really huge. These are the peak scattering to the left with spin down, spin up. And this was the opposite effect with the same spin scattering to the right. And so even without glasses, you can see that it seems to work. So let me show this nice transparency. Is from Michelle Stancari from Ferrara. She's now at Fermilab. with the addition from Dima Topokov from Novosibirsk about the ABS intensities of the different targets. So here's the Stanford source with, I think it's the Glavish source, then Madison, Filtex, Hermes, and this is the Novosibirsk superconducting source, and this is Anke, and here the world champion RIG hydrogen jet. So the magnet technology for Stanford was warm iron, Madison, the others permanent sextuplets, except Novosibirsk superconducting. There's a noise. Has it anything to do? No. Okay. Okay. So let me come to the polarized internal gas target at Web3, the deuteron experiment at Novosibirsk. And here is a design of the result of a ray tracing calculation. So these shaded magnets are permanent magnets, and this green one is superconducting magnet. They differ very much in pole tip field, 1.6 Tesla, and the superconducting one 4.8 Tesla. And this has effects for the acceptance of the magnet systems. So you can really use such a strong magnet if you have a, say, divergent beam, which you then strongly focus on a spot. And the superconducting source is sketched here. One has two groups of magnets in green. So this is green. And in blue, these are the blue magnets at different currents. And the superconducting ABS in conjunction with a storage cell is operated together with a storage cell rather flat, 24 millimeter horizontal, 3 millimeter vertical, used in Web3, as I was told by Dima Topokov. And an important measurement was done in 98, 99. The test of a dry film coated target cell in the Web3 electron storage ring at Novosibirsk. And this diagram shows the result of this collaboration between the two labs. The asymmetry AP of deuteron breakup over 8 months was found to be constant within the errors. This result paved the way for the Hermes experiment based on a dry film coated storage cell. Yeah, next project I want to discuss is Hermes. So it's the target is based on the Filtex target with Liverpool and later Beijing, Erlangen, Ferrara, Yerevan. Okay, so let's. 1993, Hermes was approved. Here you see Tom together with Kirsten Zapfel. She died some 15 years ago. And here you see Steve Pate and Wolfgang Korsch. He is now, since a long time, 15 years, 20 years, in Kentucky as a professor. So they work on installation of the helium-3 target, which was the first which went into the target position. And here's a picture of the Hermes collaboration. I think it's from end of '94, close shortly before the experiment was rolled in. So here in the background, you see the experiment, and here a large part of the collaboration. Here's Willy, and here's me. That's the guy with the tie, because I was technical coordinator of this project, and so my work was coming to an end. This is Jo van den Brand, whom you also know, and Klaus Ried, who together with Richard Milner initiated this experiment. The Hermes experiment ran at the Hera electron ring, and it has a circumference of 6 kilometers, so you have to bend the 30 GeV electrons, and they emit a lot of synchrotron power. So you need a gallery of superconducting cavities, which eat an enormous power. So in the range of say 10 megawatt continuously to replace the losses due to synchrotron radiation. The electrons under these conditions are self-polarized. That's a so-called Sokolov-Ternov effect, which was brought to a high efficiency because we do have to apply all kinds of tuning to optimum orbit and so on. And we got polarization values in the order of 60% just by this high energy. And here is a view of the Hermes experiment with a target. In this case, it's the hydrogen deuterium target, but first the helium-3 target was mounted. This is the electronic hut with electronic and also gas handling equipment, which could be rolled in common on rails. So one could, this is the beam position, that's where the beam goes. But if you would have had a problem which would not be repairable in a short while, then our experiment would have been rolled out. So, and here was a big shielding wall in between. As I said, the first target was a polarized helium-3 target by MIT Caltech. Here you see a sketch, a cold cell, a tube from the glass pumping cell where helium-3 gas was polarized by metastability exchange optical pumping using infrared laser light. And to inhibit motional depolarization, one had to have a large volume, weak target holding field close to a huge magnet. This is the problem. So the polarized helium-3 target here is shown here, helium-3 target upstream of the main dipole. The blue thing is a big shielding plate, cryogenic target cell with optical pumping cells surrounded by the field coils. And the sign of the target polarization could be switched via the light helicity, and that's shown here. This is the measured polarization in the pumping cell. This is, one can say an artist view of the Hermes hydrogen deuterium target, which I cannot explain in detail. So it's an atomic beam source, but the beam comes down this way. Here's a extracted sample beam, which is analyzed by the polarimeter. This is a beam line for the proton beam, the beam line for the electron beam. And here, this was already explained, is a picture of the helium of the hydrogen target cell with the tubes for injection and sampling. And the other explanation you already heard from Tom. The cell design and fabrication was Tom Weiss together with Jeff Court from Liverpool, and later the Ferrara group with Paolo Lenisa took over this job. And this is a picture illustrating the stability in, during the best year we had in 2000, atomic fraction for deuterium run 2000, very high value, more or less constant. Here's a vector polarization plus minus, tensor polarization plus minus. In 1999, we had a workshop in Erlangen. I want to just show this transparency. So it's a picture with Willy and Rudolf Fleischmann talking to each other. And here's a picture of the participants with 110 people, and several people in this room are also on this picture, for instance. Okay, so this is Alan Krisch, Willy, myself, Tom Kleck, that's Hans Schick, and that's Anatoly Zelinsky. I don't know, will he come to this meeting? Ah, okay. Okay, so let's skip the, this I have to show. This was the opening talk by Willy with the title Polarized Gas Targets, Medieval Warfare. So he had developed, or he had discovered a fortification in Carcassonne, France. They had a system that they throw big stones. They were rolling back and forth, multiple use of each projectile back and forth oscillation in potential value. And so he had really a lot of humor to presenting such a talk. And my comment is that the origin of the storage cell is now explained. So it's come from Carcassonne, quite clear. Okay, so let's show a few transparencies from the, yes, you will kill me, I guess. Frank, will you show anything from? Okay, thank you, very good. So then let's, this is a really nice picture which you have to enjoy. It's a very fancy target cell of the PAX experiment, and here's the PAX low beta section. So my last, I wouldn't say transparency, but project, the target for fixed target experiments at the LHCb detector with 70 eV protons. So phase 1 is an unpolarized storage cell starting now. It's called SMOG-3. And phase 2 would then be the design and construction of a polarized gas target. And just a picture. This is a design of the storage, openable SMOG-2 storage cell. This is a sketch of the LHCb experiment. And this storage cell will sit here. LHCb is the only experiment to run in both modes, in collider and in fixed target simultaneously. And here you see a view into the Velo vessel, that's a vertex locator. So there are two detector boxes and two very fancy thin-walled containers for the silicon detector. And here upstream, we have the target cell connected to the two halves which is an opening and closing with the movement of the target cell. So progress report was given by Willy and me some 15 years ago, and just let me mention my first meeting with Willy on the occasion of the 70th birthday of Rudolf Fleischmann in Erlangen, in a small place, Ebermannstadt. And at this meeting, Willy was the most distinguished speaker. Already it was quite hot. The German professors came in suits and ties. Willy preferred casual look, casual wear. Sometimes he took off his sandals and walked barefooted, to the astonishment of the younger participants like me. So it was really very impressive. He talked about shape effects in the deuteron scattering. This was later taken up by Dieter Fick's group, and I participated in this. So Willy in Heidelberg, we did some hiking in the Neckar Valley, Willy with my family, and here they are picking cherries. And so my last comment is that we deserve big thanks to Willy for his contributions to our field, and to you for your attention. Thank you.
Thank you very much, Erhard, for a fantastic talk. I would like to entertain questions. You were crystal clear. Thank you very much.
Thank you.